Okay, so today I wrote out notes, and there's a lot of notes. So what I'm going to do is I'm going to, I think what I'm going to do is I'm going to add some notes to what I'm going to write down, and I'll tack it on to the probably the beginning. I'll stick it on the beginning of the notes that you'll see me writing, and this is going to be, let me write this as pre-notes because it's going to be inserted up here. The calorimeters, just the short discussion I wrote out, and heating processes. This is really a review of stuff we've talked about before. That's section 7.4. So the first thing I'm going to start with today will be 7.5, but I'm going to do that after I go through, let's see here. I'm going to do it after I go through just a second on grace, because I sent out that email to everybody to discuss how to just add a data set that's a function, but I want to go through this really quickly. So let's say adding a data set in grace. You can do this a lot of different ways, but for the purposes of this assignment, I just want you to be able to basically put a function in. But what we know how to do so far is if you already have some points put in, you can either do a regression, or you can actually just do a function too. That's not necessarily attached to your data set, but it might not be clear how to do that. And it's a useful thing to do. So what you do is, the easiest way to do this is to go to Edit, Data Sets. And you know what? Hold on a second, because I think what's going to happen is you're not going to be able to see everything, right? You're just going to be able to see a particular window. So let me share my desktop as opposed to just trying to share the window. So now you should be able to see the data set sub window and the data window. Anytime you have a data set window, so there's no data here in this window, but if we had a bunch of data sets, you'd see the list of data sets. Anytime you have a data set window like this, you can right click, and down here you'll find create new, right? And then this really shows you all the ways that you can create a new data set. You can use a simple text editor. It'll give you a spreadsheet, right? Which actually enables you to do some formula stuff. Or you can just do a formula. So Grace is not really a spreadsheet, right? And spreadsheets are really, I don't really like to use them. Anyway, so let's go to formula, So what this is going to do is going to pop up this window. And I tested this out before class to make sure it works, but let's see what we're going to do here. This allows you to say the start and stop and how many points. The length is how many points you're going to include. Now, I will say that if you know the kind of range that you want your data to be, so here what we're going to do is do something similar to the problem set, right? So my X range is going to be temperature in Kelvin, and I'm going to run it from 250 to 850. Now, before you start, the one thing about doing this is it's not going to automatically change your axes to fit the data that you're creating. Does that make sense? When you read in a data set, you can tell it to auto scale, right? And sometimes you don't want to do that, but with your first data set, generally you do. That'll kind of set your axes generically to fit your data, but it's not going to do it here. So to make sure that we're not missing anything, let's go in and to plot and axis properties, and let's set those limits, right? So we're not going to, let's do it before we create the function rather than after. Tick spacing, it's important to do the start and the stop and the tick spacing so you don't get the annoying message that there's too many ticks. Well, this is doing this because of, these are old messages basically, because like I said, I did this before. Now, the start and stop for your Y is really going to depend upon your parameters, but what I'm going to do is I'm going to make the constant parameter of my function going to be 10. So I'm going to set this to 20, right? So in other words, normally for like a heat capacity, you're setting it to 0, but in this range, the lower limit is effectively around 10. So I'm going to put in 20 and see how that works. I'm going to change the spacing here to 5. Okay, so what's happening here? You see the axes went crazy. It's because the alt axes are on, I believe. This is kind of a pain. There, so if we turn off those alt axes, to me, the default would be nice if the alt axes were off, but that's not the way it is. All right, so my axes are set. So now I can come back to my function. Let's see, I guess maybe that I'll call that window up again. Create new by formula. Here's my window. Right. All right. So I'm just going to make something up. The constant's going to be 5. I know I said 10 before. And I'm going to have a linear term that's kind of small. Right. So my linear constant is 0.1, and then just multiply it by x. And then I'm going to subtract off a really small 1 over x squared term, right? So now I hit accept. Now, this created it, but what I want to do now is it's not showing up here. So maybe I miscalculated. Yeah, I did. See, I can see now the Y values start at 30. So I kind of missed it, but that's not unusual, right? You need to be able to know what to do if your new data doesn't show up. We just have to fix this. We'll stop this now. Let's stop it maybe at 60. Okay, so there's our data. We can now see it. This turns out not to be good enough. And so again, you might have to do this trial and error. Why? Let's stop it. We'll definitely, if we hit 200, we'll definitely stop it. But in this case, now I'm going to make the axes 25 so we don't get too many. All right, so it looks linear. It's technically not linear, right? I have a constant term, and I have, here you can see it here, I have a constant term, and I have a 1 over quadratic term. So it's technically not linear. I think if you do this with the function that's in the problem, you'll definitely see it's not linear. So this is how you do it. So it's not actually, you're not actually doing anything super interesting using Grace, but it's kind of an additional skill. And remember that using a plot, you could calculate the area under this curve by weighing it, right? You could do that. I've done this at least twice when I was a undergraduate, just kind of as a proof of concept. So that's all. That's how you would do it, and it's a good skill to be able to have, just to add data sets, right? What if you want to add a data set within Grace? You can do it that way. Okay. So let's now continue. There's a lot I want to cover today. So that's why I'm kind of streamlining this other stuff, okay? So very important kind of conclusions in this chapter. The end of this chapter kind of wraps up in a bow, let's say the first third of the course. And it's kind of profound. Now, the thing I like about Devoe is he sets the table for a lot of important things, which I'm going to mention here, but he doesn't feel like he has to get deep into them now, right? Which I think is good, because it allows you to kind of think about, you know, exactly what we're going to talk about, and get you kind of familiar with the equations and the functions, but without kind of saying, oh, and this is going to be this and this is going to be that, because then you can get overwhelmed, right? When we talk about what it actually is going to mean, you're going to be able to refer back to what we talked about, but you're not going to have the heavy weight of thinking about what it is right now, if that makes sense. So let's talk about now these tables of partial derivatives that that Devoe has. They're mostly for reference, right? So you should look at them and become familiar with them. And look for patterns. There's one thing I want to make sure you understand that you can do, because it's very useful, and I call this opening up a partial. And he mentioned this too. Let's look at a partial. I just grabbed one, dH by dV at P. There's nothing special about this partial. It's just one of the many partial derivatives in these tables, right? Well, by opening up, what I'm going to do now is I'm going to introduce a new dependency on kind of a variable that's natural. So what we're going to try to do here is introduce a t dependence into this partial. In other words, I'm going to create dH by dt, right? And this is still going to be constant p. So this is different than using the chain rule. You know, the chain rule where the three successive partials equal -1. That rotates the three variables of interest in your three-dimensional partial derivative. In generic terms, it would be x, y, and z, but in the case of h, it would probably be h, p, and t, right? And you rotate through those three, and those three rotations equal -1. This is a little bit different, right? I'm going to open up dH by dt, and that means I'm going to put dt here. So I'm kind of like dividing out, right? So it's almost like a dimensional analysis insertion. And I have to keep the two ends, right? The two ends have to be the same. And I'm just kind of inserting the t dependence. And this is all like that. So the utility of doing this is that you may have a partial that you don't know in terms of measurables. So let's say this first one, we don't know what this is in terms of the measurables. You can put it in terms of other things, possibly, if you're clever enough to put it in terms of the measurables. So this first one, dH by dt, hopefully you recognize that as CP. That's one of the ones that's hopefully very recognizable. And this other one is 1 over alpha v. So the whole thing, you could say dH by dV at P is CP over alpha V. And this you'll see this in the table. You'll see this as one of the things in the table. So it may be you don't have the table, right? And then you go to the table and see what you can come, what the result is. It may be that you do have the table, which can help inform you what you might want to use to open it up a little bit more. But it's important to realize your constraints, right? You're introducing one new variable. It could be S, you could be introducing S, who knows? But you have to keep the constant values, the P's, the same all the way through. And this is different than the chain rule. Okay, so let's now look at kind of skipping over those tables and the discussion. I think that's pretty self-evident. Let's think about isothermal pressure changes. We spent a lot of time talking about volume changes, but not so much time talking about pressure changes. This utilizes table 7.1, which is the constant T. The constant T table is 7.1. So we could call this the constant T table. Well, delta U, right, in order to work with internal energy changes, then we're going to use delta U. So let's look at du by dp at T, right? So this would be a pressure change that's isothermal. It has to do with U. We could pick H or A or G too, right? So in other words, depending on what you're thinking about. In a sense, it doesn't matter which one of these you kind of start with, because remember we had a problem or two where we are always able, once we have a function of one of the thermodynamic potentials, we can generally get another one through some relationship or derivative or whatever. Okay, if you look at the table for this, this is minus alpha T plus kappa T P, and I'm using the label name rather than the physical name for these things because it's faster. So delta U is going to be the integral of that partial, which is going to be the integral over some P1 to P2 minus alpha T plus kappa T P V dV. I'm sorry, dP. Okay, so for any one of these things we actually want to measure, we can go through here. It could be isothermal, it could be isochoric, it could be isobaric or whatever, right? So this just kind of lays out the way we might want to do this, okay? If we happen to have an ideal gas, we're always going to try to use PV equals nRT, right? And this is going to change this apparent V dependence to P dependence. The V is nRT over P, right? And so what that gives us is also some other relationships that we should be looking for. It usually gives us very simple relationships for the alpha and kappa. Right, and we also know that delta U is 0 for delta T is 0. Okay, now this particular problem, let me, there's two ways that we can show delta U is 0 here, right? This is one way. Delta U must be 0 for an isothermal process. The other way here is that the integral of P1 to P2, well, alpha is 1 over T. So this is -1, right? When we insert that. Kappa T is 1 over P. It doesn't really matter how we represent V, we get the integral of 0, right? So for an ideal gas, kind of mathematically, the integral is 0. But we're also constrained by the fact that for an isothermal process, delta U is necessarily 0. They have to be consistent, right? They have to be consistent. Okay, let's now talk about condensed phases. Condensed phases, in some sense, are harder. In some sense, they're easier. But for condensed phases, if we want to look at this process, for condensed phases, well, we have these two measurables that matter in this integral, right? We have alpha t and we have kappa t times p. Well, what are they? Alpha is the compressibility, right? And kappa is the expansivity, right? And these things have some physical meaning for a solid or a liquid. So it turns out that the I guess the first one's the expansivity. This is why I don't like using the names, because I can never remember them. This is true. The alpha times the t is much greater than the kappa times the p for solids and liquids, kind of for two reasons. The first reason is that this kappa is roughly constant, and that P is typically 1 atmosphere for a condensed phase. In other words, we're not really interested in the ambient pressure. So, and I think we'll see this more explicitly in a few minutes, but what this means is that we end up with a different set of constraints on our condensed phases, right? Okay. Let's now talk about standard states. Okay. So one thing we want to realize in thermodynamics is that pressure is of utmost importance in thermodynamics. For now, let's suffice it to say that we do a lot of work with gases. One of the reasons we do a lot of work with gases is that we can always kind of fall back on an ideal gas or compare things to an ideal gas, which is a lot what we're going to do today. So this might be the first reason why pressure is of primary importance to thermodynamics, but it turns out to be important for solids and liquids too. And that's because pressure, vapor pressure, is what connects different phases of the same substance, right? This allows mass transfer between them and so on. So pressure turns out to be really important. So let's define a standard pressure. We're going to call this P naught, right? We're going to define this as 1 bar, right? And in terms of the SI unit, this is 10 to the 5th pascals, right? Or 100 kilopascals, right? And so this is slightly less than an atmosphere, right? Because an atmosphere is 101.3 kilopascals. So this is 1% different from an ATM. So one of the things that is frustrating or unusual for students is the physical chemists work with a bar. The reason the physical chemists work with a bar is it is an SI unit, right? So it has a connection to a Pascal. So you don't have to convert between liter atmospheres and joules and so on, right? A joule is kind of inside a bar already. Okay, so Devoe talks about different definitions of standard states. This is not super unusual for solid or liquid, but let's start by talking about a gas, because for gas it is a little bit unusual. A gas standard state. A gas standard state is standard pressure and a temperature of interest, right? So it turns out that standard states are never defined. I'm sorry, temperatures are never defined with respect to a standard state because it's the pressure that's important. I know you're used to seeing things like delta H standard 298, but the fact that this is labeled with the temperature does not make 298 a standard temperature. There's really no such thing. It just tells you that you're looking at the standard state at 298 K. So it's usual to pick a standard, it's usual to pick, I have to watch my language carefully, right? It's usual to pick a convenient temperature, 298 K, 25 degrees C, but it's not really a standard temperature. It's just a convenient temperature that we live in, right? 298. Okay, so we look at standard pressure, 1 bar, and whatever temperature we want, right? And the definition of the standard state is where the gas behaves as an ideal gas. All right, this is hypothetical. It may turn out that we can find these conditions where our gas acts like a real gas, but it may be our gas never acts like an ideal gas. So it's hypothetical, right? How do we define this? We turn off the intermolecular forces, right? Of course, we can't do that. But if we could turn off the intermolecular forces, then we would have an ideal gas, right? So that's kind of the full circle, right? Okay, so in this case, the molar volume, right, V over N, approaches RT over P naught, right? 22.4 liters. You probably know what the value of this, 22.4 liters at 0 Celsius or 273 K. But again, the temperature is kind of irrelevant here, right? The temperature can be anything. We're not really putting a constraint on the temperature. Okay, for solids or liquids, this is actually easier, right? The standard state, the language is a little bit weird, but it's actually, if you think about it, it's something where the standard state is useful. The solid or liquid standard state, the condensed phase standard states, are the unstressed condensed phase at P naught and the temperature of interest, okay? So we say it's the unstressed or equilibrium phase at our standard pressure and our temperature that we want to be at, right? May be stable. Oh, I'm sorry, I'm saying this wrong. May be a real state if stable. This is very common, right? May not be real if unstable, right? Could be metastable too. For example, a supercooled water sample is metastable, but we could also define the standard state may not actually be stable at the temperature we're interested in. But often, we might even say mostly, a real state. In other words, we don't have to come up with a hypothetical state to define the real state, right? On the other hand, this means the forces are actually going to be an important part for the condensed phase, so that it might turn, the definition here is easy, but the math might be hard. For a gas standard state, the definition is hard, but the math is easy. Okay, I don't know if that makes sense. All right, so let's now talk about the meat of this lecture today, right? This is chemical potential and something called fugacity. Fugacity is going to be our introduction to non-ideal behavior. So chemical potential has one definition. There's a number of definitions, right? It's the molar volume, right? Which is G over N. Other definitions, just so we know, other definitions are things like dG by dN at P and T equals mu, right? So this particular partial definition that I chose looks like molar volume, right? The free energy change per N is really another way that you could define molar volume. But these types of things come from the thermodynamic potentials, the total differentials that we get, right? Okay, so other relations are useful to be able to get. These types of things are the partial of chemical potential with respect to temperature at constant P is minus molar entropy. So one of the useful things about using chemical potential is these are always going to be molar quantities per mole. So it really doesn't matter if our system is open or not, because the quantities are defined per mole. Okay, another one is d mu by dp at T. This is the molar volume. So these chemical potential derivatives are very useful because they give us some state functions, right? So let's look at this. Let's look at the second one. Molar volume is always 0. This is a physical requirement. The molar volume cannot be less than 0, so it's always positive definite. This tells us what? This tells us that chemical potential increases as pressure increases. So in other words, we could draw a cartoon figure, right? Right off the bat, mu versus P looks like this, or this, or, you know, we don't know exactly the nature of that curve, but it's increasing. This is going to have important ramifications later, right? This is one of the things that, if we understand just this relationship, it's going to have profound implications as we look in the low pressure limit. Okay. Okay. So let's talk now about standard chemical potential. We're going to call this mu naught. All right, so the standard chemical potential, this is going to be the chemical potential in a specific phase and the temperature of interest, right? And it's going to have to do with the standard state. So the standard chemical potential is going to depend strongly on the state or the phase, right? And this again is going to be at our standard pressure always, but the temperature could be anything, right? So the standard chemical potential is still a function of temperature, but the temperature dependence in general is straightforward or something we can figure out. Okay, we have the limitation that chemical potential cannot be known absolutely. In other words, if chemical potential is really the Gibbs free energy recast, we know that for all thermodynamic potentials, we cannot define these absolutely. The only thing that we can define absolutely is the entropy, right? Entropy is 0 at 0 temperature. But for everything else, we can only define some difference. So let's call it delta mu can be defined. Okay, so what that means is we're gonna start by focusing on some change or some difference. For example, relative to the standard. Okay, and what we're going to find out is that we at a certain temperature we can define a standard chemical potential, and that's going to be a constant. But for now, we're not going to worry about that. So, okay, so let's work with the conjugate of pressure. This is, of course, volume, and let's work with molar volume. And so what I want to do is remind you that we have this up here, right? So we have this relationship between chemical potential, pressure, and the molar volume, which is very handy. So let's kind of break out that partial derivative, right? And then we can say d mu is Vm dp, right? And this is at constant temperature. So the change in the chemical potential with the pressure change is proportional to the molar volume, right? So let's now say that a change from some pressure away from the standard pressure relative to the standard pressure, right? We're just going to call this, right? So in other words, we're going to call mu naught the chemical potential at the standard pressure. That's the standard mu. All right, this difference, whoops. Notation in physical chemistry is hard, right? This can be written as going from P naught to some P prime Vm dp, right? All right. So this is general. And to be able to look at this, let's start with gases. Because recall the definition of the standard state for gases is kind of wonky, but once we get past that, working with them should be doable, should be doable to work with gases, right? So let's define mu naught G. This is going to be the gaseous standard state. Now, of course, if we're going to deal with gases, we're going to define the standard state relative to the gas standard state, but we're kind of introducing a new notation here, right? This is the gaseous standard state chemical potential. This is going to turn out depending on the gas that we have, it's going to be a constant, right? Because it's a fixed pressure for a fixed substance. So it is a constant. We just might not know what that constant is at this point. For an ideal gas, V over N, which is the molar volume, is RT over P. So these two things, Vm equals RT over P, is going to be a standard substitution or something we're going to want to recognize, right? And the standard state is when P equals P naught, some general P equals P naught. So what we have, using the above equation right at the top of this page here, the chemical potential at some pressure minus the chemical potential at the gaseous standard state, P0 P RT over P dP, right? This is fairly easy, right? RT log of P over P0. Or we could say that the chemical potential at P is some standard chemical potential plus RT log of P over P0. This may look a little bit familiar to you. This is, in freshman chemistry, a starting point for defining equilibrium constants in terms of pressures. Okay, but we're gonna move through this very slowly. And of course, we want to label this. The restriction here is that we have an ideal gas. Okay, for real gases, this is we're kind of limited here by the standard state, right? Because it's hypothetical. And I keep saying this, right? IMF off, right? The intermolecular forces are off. So the first thing I want you to realize is the pressure for the real gas is not the same as the pressure for the ideal gas, right? This should be clear. And we might want to kind of take an extreme case, right? You might want to think about water vapor or ammonia vapor that, you know, has hydrogen bonding and strong intermolecular forces, where clearly the pressure of an ammonia gas is going to differ from an ideal gas of the same mass and the same temperature because of the forces, right? So this should be clear to you. So let's call this real gas pressure F, and we're going to call this the fugacity. right? Okay, so if we do this, then we can say mu is the standard chemical potential plus RT log F over P naught. Okay, so what I'm doing here is the reason I'm changing the real gas pressure to some variable is because what I want to do is I want to relate this to the ideal gas pressure, and it's going to be different from the ideal gas pressure by some factor. I don't know exactly what that factor is, but in other words, I don't know if F is greater than P or F is less than P, but at this point we don't want to limit ourselves. We just know that it is the real pressure, right? So that's the confusion here, is why am I calling the real pressure something different? Is because I want to relate this to the ideal gas pressure, which I can figure out pretty easily, right? Does that make sense? So I'm going to rearrange that equation into this. I'm going to solve for this fugacity, and I can say the fugacity is the standard pressure times the exponential of mu minus mu zero in the gas reference over RT. So let's look at this, all right? Because what we can say now is, if we look at the equation this way, this sets the pressure units, right? In other words, P naught sets the pressure units. If we want to work in atmospheres, we can just do a unit conversion between bars and atmospheres, right? But this is unitless here. And what it is it's the free energy difference between the real state and the hypothetical state, right? So the free energy difference between the real state and the hypothetical state. And so this is this kind of equation or relationship we're going to see a number of times, and it's very, very important. So F has units of pressure, but what it is it's kind of an effective pressure. So fugacity can be seen as the virtual pressure, right? The virtual pressure that the hypothetical ideal gas, in other words, IMF off, I keep saying this, I'm just trying to emphasize it, would need to have in order to have the same chemical potential of the real gas, right? Okay, so I'm going to say the chemical potential of my real gas is this, and it has a certain pressure. Now, my ideal gas is a reference, and an ideal gas is something I know how to work with really easily. What would the pressure of this ideal gas have to be to have the same chemical potential of my real gas, right? That pressure is the fugacity, okay? So it's a virtual or an effective pressure, right? In other words, it treats the real gas as an ideal gas at an effective pressure F. That's what the fugacity is. So it's an effective pressure. Okay, so we're going to start to work with the fugacity and understand what the fugacity is with some simple relationships and examples. So how may we evaluate the fugacity? Okay, there's two main ways for now. The first is a derivation in Devoe. I'm not going to explicitly go through this for two reasons. Let me explain the two reasons why. The first reason is I was afraid I wouldn't have enough time to go through the derivation, and it is in Devoe, and sometimes these derivations are difficult to understand. I don't think this one's super difficult to understand, right? So I may go through and write this out a little bit more explicitly in a little bit different way than Devoe does, right? But what we get is the log of the ratio. So this ratio or relationship between these two is going to be important. Okay. So this kind of makes sense, right? In other words, if you just think about the ratio of F over P, right? When will our real gas act the most like an ideal gas, right? In terms of pressure, we're not going to think about temperature now because there's a temperature limit too, but let's think about the pressure. When will a gas stop feeling other gas molecules of the same part? At infinite dilution or zero pressure, right? If the pressure is zero, then the distance between the gas molecules is infinity and there's no forces felt. So the fugacity and the pressure should go towards 1 as P goes to 0. So we have this dual limit, right? We have this dual limit, right? In other words, intermolecular forces go to 0 as P goes to 0. These are all different ways of saying the same thing, two different ways of saying the same thing, right? So that means the logarithm of F over P should go to 0 as P goes to 0. And another way to say this is that the difference between Vm over RT minus 1 over P also goes to 0 because these two things are the same thing in the ideal limit. So this is just a bunch of different ways to say the same thing, and whichever way, the more mathematical way or the more physical way, which is really this last thing I wrote down, is okay. We can also define what we call the Fugacity coefficient. This is given the symbol phi, and this is the ratio of F to P. Why would we want to do this? Well, what this kind of does is it wraps all the non-ideality into one package, right? In other words, if we use some reference gas or reference pressure, we may only know the deviation from that reference pressure. We might not know the absolute of one or the other. Or on the other hand, we may not have to know the absolute pressure if we use a reference pressure, right? Or a reference. So this is using a reference to avoid having to calculate something directly, right? And sometimes looking at the fugacity coefficient is more enlightening than F itself, right? It's like, you know, when people say, you know, lots of times, whether it's a poll or some data that somebody releases to the public and says, well, you know, we gained 5,000 jobs this month. And if that's for the whole country, then the relative job increase is like nothing, right? I mean, that's effectively zero. If it's in the county, that might be awesome. So it's the relative thing that usually gives you more information because it instantly gives you a frame of reference. And that's one thing that scientists or people who've thought about stuff, you don't necessarily have to be a pure scientist, right? You could be a social scientist, right? But you're used to looking at data this way in a relative sense, and it's very important. And we're going to use this over and over. This is similar to Z, which was P. Well, I can't. Did we use Z this semester? I can't remember, but we definitely use it in freshman chemistry. Z is the compressibility coefficient, and Z equals 1 for an ideal gas and shows deviations. All right, so if we define the fugacity coefficient this way, then what we can say is the fugacity is the coefficient times the pressure, right? So it gives us this factor on the real pressure, and we would say that the fugacity coefficient goes towards 1 as pressure goes to 0, right? So this is kind of useful because now we would say if we know what the fugacity coefficient is and it's close to 1, then we know we can use the ideal gas approximation, right? Okay. So then what we get for the expression is, if we want to say calculate it, it actually gives us a way to calculate it. It may not be exactly clear at this point, but if we calculate the molar volume and the pressure, then the difference gives us the fugacity coefficient, right? So we could experimentally calculate the molar volume at a certain pressure, and it gives us the fugacity coefficient. Okay. So let's look at a really quick example. We're actually going to do more work with this and more examples in the coming chapters. We just want to kind of germinate this for now. If we use a virial expression, remember a virial? If we use a virial expression and stop it at one term, then we get this. Vm is RT over P plus B, where we can see B is some correction, right? So this is another way we thought about ideal versus non-ideal gases, right? If B is 0, then we have an ideal gas. But in general, all gases have this B correction term. What we can say then is that the log of the fugacity coefficient is approximately BP over RT. And if you put this into here and integrate, you should be able to come up with that, right? It's not a hard integration. So we immediately have the ability to calculate this fugacity coefficient is a function of temperature, right? It's BP over RT, and really, I should say the fugacity coefficient as a and really you have to be careful because the B is a function of temperature, right? But anyway, you can see that maybe we can calculate this fugacity coefficient. So the final thing for today is standard molar quantities. This is actually something we've worked with before. I don't know, Devoe, the framework that Devoe provides for teaching this stuff is to introduce something and work with it, and then later on you might actually find out what you're doing. You might like that, you might hate that, I don't know. I'm going to be interested to see what you think at the end of the semester. But let's think about this for a minute, right? Because we know that the standard state of a gas, right, is hypothetical. But now that we've defined this thing called fugacity and we have it in terms of the chemical potential, we'll use chemical potential. Its relation to GM, it's really the same thing, right? Fugacity and our thermodynamic relations between potentials to find all the other thermodynamic potentials for a real gas. Right? All right, so for example, the chemical potential at some pressure is going to be the standard chemical potential using the gas standard state, the hypothetical standard state, plus RT log of the fugacity, which is going to be some function of pressure over the standard pressure. Okay, well, we can break this last fugacity term up into two chunks, right? We can say that this is the standard chemical potential plus RT log of the P part plus RT log of the function, the fugacity part. Okay, so what is that? Okay, so now what we can do is substitute our expression in for the fugacity, right? So in other words, we get this new chemical potential, or this chemical potential of interest, let's say, is the standard chemical potential in the gas phase. Whoops. So the point is, we have some expression. So this immediately gives us Gibbs free energy, right? Because these are really one and the same. In other words, we can say the Gibbs free energy at some pressure equals some standard Gibbs free energy from the gas phase plus a pressure dependent term, right? So the first thing is a standard free energy, which is going to be a constant, right? This is the part we don't know where it is absolutely, right? But we do know it to within some constant, and that's the constant, which we may or may not be able to figure out, right? But it's just a constant. Doesn't change the behavior, like the way the line or the function looks. It just changes where it is up or down. Then this first term is like an ideal gas term, right? And then we have a term that shows us the deviation from the ideal gas. Right? So we have a standard, a constant term, we have an ideal gas part, and then we have some deviation from the ideal gas part. And that's what this gives us. And the reason we had to go through chemical potential is because we defined the fugacity, we defined the deviation through the standard state and the chemical potential. But now once we have that form and relate it back to Gibbs free energy, we can use different appropriate manipulations, right? And we've done this before. We just haven't done it for chemical potential. This gives us in Devoe table 7.5. Table 7.5 shows us the result using this free energy expression for all the other ones, right? And the way we get that is that the standard molar entropy, for example, is minus d mu by dt at P. The internal energy is the molar Gibbs free energy plus T times SM minus PVM, right? We did this on a problem set. Remember that one problem where you just had to do a bunch of different derivatives? So once we have this analytic expression in terms of free energy, we can get all the other ones. But in order to get this non-ideal part, right, this part here is really the non-ideal part. We needed to go through chemical potential. Okay, so finally, it's always good to have an approximation as a starting point, right? And that might be using this simple virial expression, right? So this is the approximation. The approximation is using this virial. This leads to the approximation for the chemical potential. Right, the ideal part and the correction. So again, it's always good to have the reference. In this case, the reference is the first two parts, and this is a correction. So let's put this into the context of a plot, because you know physical chemists love plots, right? Here, if we're going to have the chemical potential for some hypothetical substance, then we have this. This is going to be our reference, right? This down here is going to be the mu, the standard mu. And if the real behavior like this is going to be our correction. So the reference is going to be the ideal, right? So in a sense, what we're doing for this kind of setup, if we look at the chemical potential this way, then we're always going to have an ideal reference, and we can calculate this as some deviation from the ideal, which is kind of useful. And we're going to know if the reference is higher, or I'm sorry, if the real is higher or lower than the actual. And once we have the chemical potential, it allows us to get all the other thermodynamic derivatives through the Gibbs free energy. Okay, so this kind of sets up the middle third of the course. So the middle third of the course is we're going to be working with this stuff to try to figure out some phase behavior and understand some thermodynamics of phase behavior. The last third of the course is going to be kinetics, which is kind of totally different, right? But that's kind of where we're going. Does anybody have any questions? Trying to take this kind of slow because it can be overwhelming. Okay, so looking towards next week, we'll have it. We'll have the test on Monday. Take home, and what I'll do, the problem set. I'm looking at this schedule again. The problem set will be due Sunday night. Sunday night, I will gather these and grade them and get them back to you by either late Sunday night or early Monday morning. And then we'll have the test. And the test will be, I think the test will be due midnight. I don't want to make it first thing in the morning because I don't want you to work on it all night, because that's never good. And it shouldn't require you working all night, right? It should still be, remember my goal is that if we all came to class and sat in the classroom for an hour and 15 minutes, you'd be able to do it. You'd be able to get it done with the appropriate stuff. So again, I feel like the problem sets are harder or require more intense kind of work than the test. Okay, that's my goal. Okay, so as always, if you have questions or need help, just let me know. I'm willing to do a Zoom or whatever if you need it. And until we meet again, I will see you. I hope you have a good weekend.
Will the test have graphing on there?
Possibly. So it might be possible that you have to do a plot. That is one thing that I can't ask you in an in-person thing. So that's actually one thing that I'd like, that I can ask you to do a plot. And those things can be time consuming, right? But usually doable, and it can be more satisfying too. I think that you can actually plot something and extract some data. So yeah, you might want to look for a plotting problem on there. Good question.
Thank you.
Okay.